All right, thank you, Michael. Nice to be here. I'm going to talk today about some work in a paper by myself and these two recent students. I'm very proud of these two students, by the way. Justin Dyer did some work that I think will help people figure out how the sample graphon approaches the target graphon. That's pretty interesting. Zhou did most of the work on this. It's her dissertation. And she's now at LinkedIn, where they do have a network to predict on. So here's a sketch of the kind of problem we would like to solve. There's a network, and there are labeled vertices. Here it's spam or not spam. And most of the vertices are unlabeled. Okay, so you could imagine Facebook, and somebody liked some. They don't have dislikes, but somebody has a goldfish, and somebody just hates goldfish, and most people don't say anything about goldfish. And then you want to predict at the unknowns using the labels that you do know. And the idea is that people are likely to be connected to other similar vertices. Of course, there are covariates you could put in, and the model will allow for covariates, but as usual, if you're trying to model the graph structure, you study what would happen if all you had was the graph structure. Here's the one-slide summary of what happens. A lot of those graph-based predictions we found in the literature were linear in the knowns. I'll predict this unknown using something, linear combination of the knowns. If there's a linear combination, you think somewhere there's a Gaussian story. There's a covariance matrix, because with a Gaussian, your prediction at the unknowns is a linear function of your knowns. So we went looking for their correlation matrix. So let's find the correlations that are implied by these algorithms. Then let's replace those correlations by sampled correlations. So we can actually measure, we have a small number of pairs of labels. We can see how the correlations really are on the graph at whatever distance or similarity measure. And then we'll rip out their implied correlations and pop in our empirical correlations. So that's the idea that we're doing. We're doing it on small graphs. In this talk, I'll show you small graphs, bigger than Zachary's Karate Club, but not that much bigger than Zachary's Karate Club. In her dissertation, Zhou also looked at the Wikipedia graph, which is way bigger than Zachary's Karate Club, but not as big as what she has at LinkedIn. And we got the Wikipedia graph from David Gleich. Okay, so why does this make a difference? Well, those semi-supervised learning methods we looked at were based on the graph Laplacian. The graph Laplacian is interesting, but it's not a magical object. Likelihood is magic. Graph Laplacian is not magic. And there's no way that you could imagine that the same correlation structure should be true for people's age, their weight, their income, their BMI, their gender, all of those things. Why would you have one correlation for all of those possible responses? That can't be right. And the graph Laplacian took the correlation structure right out of the network. Okay, so that's why we think it makes sense to pop in some empirical ones. Here's some notation. So there are edge weights. They could be binary or not necessarily binary. And then everybody has an out degree and an in degree, the volume of the graph. There's a response value at vertex I. And the important thing in our notation is to separate the ones that we know from the ones that we don't know. So a superscript 0 means we measured it, and there are R of those. And without loss of generality, it's the first R of them. Then the remaining ones are in this vector y1. Okay, so there's a small number of measurements and a huge number of non-measurements ordinarily. So here's a graph random walk. Given those edge weights, we can make a transition. We can make a Markov chain with a transition matrix. That transition matrix will have a stationary distribution. We may have to add teleportation to make that happen, but we'll suppose that there's a stationary distribution, famously called PageRank now. An important object we need to use is the graph Laplacian. The graph Laplacian, it's the out degree of I minus the diagonal. This is what you get along the diagonal, and then you get this on the off diagonals. So why is it even called a Laplacian? Imagine that the vertices are 1 to n, and you have some function at all of the vertices. The graph Laplacian at vertex I is this weighted sum of differences between I and its neighbors. If you imagine the simplest graph, if your graph would look like this, just connected dots, then the graph Laplacian would turn out to just be minus a curvature at observation I. And if your graph would be a grid, it would just be like a sample Laplacian. So there's a real reason why they called it Laplacian. And it's quite interesting, but we never believed that it had magical powers. So here's one of our starting points, this paper by Zhou et al. And they defined similarity between nodes. So similarity, it's your chance of starting at vertex I and then going to j, plus your chance of the reverse trip. If that number is high, then vertices I and j are similar. Then they make up a variation functional for how rough the numbers z are. And it's a quadratic term where you weight things that are similar. So if they're not similar, you don't care if you don't care if they have comparable z values. And then there's this funny division by square root of PageRank. One way that's explained is if a vertex has an enormous PageRank, then you don't have to regularize its value of z as hard. But if it has a tiny PageRank, then you do want to regularize it a bit more. The criterion, they try to minimize this roughness, and then there's a penalty. And the penalty is your predictions can't be too far from this quantity y star. And y star is either the observed value, plus 1 or minus 1, say, or a default value, which might be 0 for all the ones where you don't know. Okay, then you have to choose lambda, and they trade off fit to observation. Fit versus smoothness is just a choice of lambda. The result ends up being a linear combination of y stars. So if they've got a linear combination, somewhere there's a Gaussian, somewhere there's a correlation matrix. If you're weighting things by a correlation matrix, you're doing what's called Kriging. Kriging was developed in the mining literature in the 1950s by Kriging. So imagine you want to know how much gold is there underneath that question mark. And you've measured how much gold there is at all these other points. And your guess will be a weighted average of the neighbors. You'll put a little bit more weight on the 1.9 than the 1.7 because it's closer. You put a little bit more weight on the 2s than on the 1s because there are 3 observations down here, and there's only 1 observation up there. But you don't put 3 times the weight here because there's a little bit of redundancy. So what should actually be your weight? Well, if you can postulate a covariance matrix amongst all the knowns and the unknown, then you can just predict by conditional expectation. So here's our Kriging model. The observation at a vertex, or this is a vector of all observations, is a linear model. We'll use pretty trivial linear models, plus IID noise, plus some spatially correlated signal. So in this regression, we'll just have a regression with one predictor. And it'll either be the square root of the PageRank, or it might just be the intercept term. Our noise will be independent. So a diagonal covariance matrix. And then the interesting correlated part is the signal. So that's the part that says how similar are different vertices in the graph, depending on how close they are in the graph. In the end, I'll skip some of this stuff. We're going to predict at the unknown by its expected value given the vector of measurements we made. Okay, so that's how Kriging works. The matrix algebra, it's in our paper. I don't want to dwell on that. So now, actually there's one thing I do want to dwell on. It's back here. The coefficient beta has a Gaussian prior with a variance 1 over delta. We're going to let delta go to 0, and that will put a diffuse prior on the regression. Okay, so here is the ZHS method in more detail. They take the similarities and they make a graph Laplacian of similarities. Then, if you decide that your noise variance would be scaled identity, the signal covariance would be square root of page rank, diagonal matrix, Moore-Penrose inverse of the similarity-based graph Laplacian, then back into the square root of the page rank, and your predictors are square root of the page rank, and your defaults are some multiple of page rank. Then you take the limit of a diffuse, you do Kriging, and you let the prior on beta become diffuse. In that limit, you get back VHS. Okay, so now we know what correlation they're using. Okay. They didn't have to derive it using that correlation, but we can find out what they're doing. It's as if you had that correlation. Okay, so it's a kind of Kriging, and the correlation matrix depends totally on the graph. One size fits all, no matter what your response is, that's the correlation. It also anticipates that the response should be nearly a linear function of the square root of the page rank. I could imagine that not every response should be linear in the square root of the page rank. Another method at the same time, Belkin, Matviva, and Nayogi, they take a similar formulation, but they're quadratic. They use the graph Laplacian itself. They didn't do similarities. Their penalty is only the prediction you made where you knew the answer minus the known value at that point. And there's a penalty parameter lambda. They don't force it to interpolate. After all, some of those labels could be wrong, so you don't want to necessarily interpolate. They're also doing Kriging. And we exhibit, what their noise covariance is, what their signal covariance is, what predictor they're using. They're just using the intercept term. And then they have two limits. An earlier work by Zhou et al. For undirected graphs is also Kriging. Also, you need this diffuse limit. Okay, there's more examples, but what I want to show you now is what did we do differently. The Zhou et al. Paper, this is their correlation structure. The other one we call Tikhonov smoothing. It has this correlation structure. And what we did is we kept the mean. We kept this diagonal matrix on the outside. We kept this diagonal added noise. And we added an empirical correlation, some sigma squared r, where r is a correlation matrix. So we have to learn that correlation matrix. And Michael wanted to know what are like the loose ends or the areas for further research. Well, one of the things that we do is make a couple of slightly ad hoc, computationally convenient things. And there's room for something a bit more principled than what we did. We want the correlation between two vertices with similarity Sij. Well, we use the variogram. We look at what's the expected difference, expected squared difference between two vertices, and we equate it approximately to the observed squared difference. That's going to be an extreme overfitting, and then we smooth it out. And we smooth it out in kind of an ad hoc way. The model gives you this formula. The important thing is Rij. We'll equate what the model says the variogram should be to the actual variogram. We can back solve this, plug this in, back solve for Rij. So we back solve and get a naive thing. We fit a spline to say what are these naive correlations as a function of similarity. Pop them into a matrix. The matrix might not be positive definite. We would actually like it to be positive semi-definite. And so then we force it to be positive semi-definite. Just bonk any negative eigenvalues up to 0. We have an alternative version where we just use a truncated SVD. Rank 1 or rank 5 were the two cases we looked at. And then we do Kriging with that estimated matrix. Oops, sorry. Here are all these, here's similarity. And here are these naive estimates of the correlation for all pairs of labels. So it's really a mess. And if you smooth it, you get this red curve. And at very great similarity, they're quite correlated. As the similarity decreases, they become less correlated. Interestingly, at the minimal similarity, it pops up a little bit. We thought it might be monotone, but empirically it wasn't monotone. Here's that same red curve again. And after we forced the correlation, after we forced positive definiteness on the covariance, we got these dots, which aren't quite where the red line is, but they're close. We ran this on a couple of examples. One of them is a data set of UK universities. The edges count how many links did University I make to University J. So maybe Oxford links to you a bunch of times, and you link to Oxford a bunch of times. Maybe Oxford linking to you is a bit more informative than you linking to Oxford. You know, I could link to Oxford from my basement. That doesn't make me a great university. So, so the edge, the directionality is quite important in this case. And the response is a research score. So somebody scored research quality of these universities. There must be a bit of subjectivity in coming up with those numbers, but we take them as given. In our experiment, we would randomly hold out some universities, maybe 10% of them, or maybe 90%. Holding out 90% is sort of closer to what we're trying to achieve. And then we'd predict the held out scores, find the mean squared error, and repeat this 50 times, just to make sure we didn't get a lucky or unlucky holdout. And then the methods we used are the two that I showed you, random walk smoothing and Tikhonov, and then our empirical correlation versions of both of them. We have two tuning parameters. We've got to pick lambda and sigma. Those methods only have one tuning parameter. But if you're cross-validated, it's still a fair competition. And in fact, in the end, we found their best value of their tuning parameter. It didn't matter. You could just arg min over the space, and they still didn't do that well. In the Tikhonov case, it was defined for undirected graphs, so we symmetrized the graph. That should be a disadvantage on the university data, to symmetrize the graph. And you need to know what's this default that we plug in for the unknowns, and we just use like a weighted regression to get some default. Recall, this is the thing that the random walk method is trying to minimize. And we found empirically that it ended up really liking the regression variable square root of PageRank. So the responses on the UK graph came out basically proportional to square root of PageRank. And what that means is that vertices with the same PageRank are going to get pretty much the same prediction. It almost totally ignored the similarity. So here are some empirical results. First, for the university data, if you use the random walk smoothing, the first thing you could do is just plain regression on square root of PageRank. And you can hold out 10, 20, 30, 40, up to 90 of the universities, and you can look at the mean squared error in your predictions. And you will see that these mean squared errors rise. The more you hold out, the worse the predictions. The red curve is the random walk smoothing with the best value of lambda that we could find. The black curve is if you just did a regression on the square root of PageRank. This green curve is our empirical stationary correlation matrix using a rank n, SVD. We also tried a rank 1 SVD, and that's the dotted one, and a rank 5, which we thought might capture a little bit more. The Tikhonov smoothing, it doesn't use the direction of the link, so it seems to be at a disadvantage here. And here is just a regression on the intercept. Here is what they get with their best value of lambda, and then here are the empirical correlations. So if you pop in sample correlations, you get a bit of an improvement. A question?
What are the measurements on the universities that you're trying to predict?
The measurements we're trying to predict are somebody's estimate of the research quality of the university on a scale that goes from about 0 to about 6. And we didn't delve into whether those were, the true quality of the university. So maybe we're just modeling how somebody's opinion varies across the graph. Let's zoom in where 50 of the universities are held out. Okay, so if you hold out 50 of the universities, the mean squared error for these two models looks like so. The baseline is just doing the regression and not even looking at the graph, just regression on PageRank, regression on a constant. The random walk algorithm improves by about 3.8%. Empirical correlations make a bigger improvement. Here's a rank 5 version and a rank 1 version. And we see even bigger improvements on this side, but it starts off from something that's much worse. It left more room to improve. Second example, maybe it's a bit overused, it's the WebKB data from Cornell, and the response we're trying to predict is whether a page is a student's web page or not a student's web page. And then we use a binary graph. Here, sort of the same kind of thing with the random walk smoothing. Now, because we're predicting a binary, we're not going to report mean squared error. We'll report 1 minus the area under the curve. And if you would just guess, you'd hit this black line. And if you use random walk smoothing, you hit this red line. And it seems like, well, the more you hold out, the worse it gets. And the empirical versions are making some kind of an improvement. The Tikhonov smoothing, this is the one that ignored the direction of the edges. Interestingly, if you ignore the direction of the edges, you're beating this one that looked at the direction of the edges. So that was kind of a surprise that ignoring the direction of the edges would help you. But maybe it has to help you sometimes.
Did you say you're using just Cornell, or you're all 4 schools in Kriging?
I think this data was just from Cornell. It was a few hundred. It was a pretty small data set. But it's also possible that we got the data from Cornell and they had all the other ones in it. But I think it was just the Cornell. So here's similar numbers. So you can score some improvements by using the empirical stuff and changing the rank from full rank to rank 1 and 5 seems to still leave you with an improvement. Okay, I'll tell you a little bit. These are things that Ya did in her dissertation. So she looked at some examples in biology. The trick there is that they don't necessarily believe there are edges in biology. And she also looked at Wikipedia, where you're trying to predict whether somebody links to the page for France. And so basically you're predicting the presence of an edge as if that would be a response on the graph. So she worked on some of those things. Scaling issues, you don't really want to do an SVD on the whole n by n, but a low-rank SVD would work. And she also implemented some Markov chain iterations where you'd run a Markov chain with killing and then use averages from that to make your predictions. And let me see. So by now, the Wikipedia graph, much larger than Zachary or much larger than the UK university, still not as big as the Facebook graph. Wikipedia graph will fit on your own single computer. And she started looking at, sparse SVDs and truncated SVDs. Here's an interesting fact that she found. So if you would take one of these networks and measure how smooth it is. So here's a protein network, and there's how the roughness it was, one of these roughness measures. And then she permutes the data at random. And the roughness measure traces out this near Gaussian, and she showed a central limit theorem, this near Gaussian roughness measure if you would randomly scramble the labels. So it's interesting that the true graph is quite a bit smoother than what happens when you randomize in the protein world. Not so in a web spam example. Whoa, quite different in Wikipedia. Every time you randomly permute the labels, you make the graph much smoother than the original one. So that was kind of an odd finding that she got, that maybe these smoothness measures might need a little bit of tuning. Okay, so I think I'll stop here and take questions if there are any, and thank you all for your attention. Yes. Oh.
In the evaluations you did, it looked like the data that you held out was missing at random.
Yes.
And in some social situations, I can imagine that the data is not missing at random. So I'm wondering if you have thoughts about how that would affect the results.
Wow, that could radically change everything. And so that's one thought. I know. There are people that try to solve. Well, actually, you spoke about this on Monday, and then people like Dean Eccles at Facebook tries to worry about these kind of issues, and I really have no great idea how to solve that.
I just had a question about when you do a holdout, when you only have about 100 nodes and you hold out 90 of them. Do you have enough pairwise samples to come up with good correlations?
So maybe we're holding in like 17 universities or something like that. The whole inset is actually quite small.
Right.
And then there's some theory, if you have 107, well, so you held in 17, but now you have 17 choose 2 pairs of differences.
But they're not all linked to, are they? And so
Well, you have a similarity measure for all of them. So the number of similarity pairs you get actually grows reasonably fast. So we were kind of surprised that you could do anything if you held out 90 of your 117 universities and tried to predict. But it seemed to work reasonably well. And then there's some asymptotics we cite in the paper that Peter Hall worked out. What happens if you try this kind of smoothing and you have on pairs of data? And it's almost as if your sample size would be like R choose 2.
okay.
Yeah.
So if I understand correctly, you're combining the Laplacian kind of covariance matrix with the empirical covariance matrix, right?
Yeah, so what we keep is that there's a regression on a predictor,
Right.
and then we keep that there's a scaling factor, a diagonal matrix on the left and the right, and we keep that there's a diagonal noise, but then we jump in and we rip out the old correlations and put in our new ones.
So I wonder whether you explore other ways of combining them, because this Wikipedia page, I mean, you have 2 components. If they're kind of in sync, it's one situation. If they're really kind of orthogonal, then you
Yeah.
might want to combine them in different
Yeah.
way.
I totally agree. We've only done the 2 examples I showed you here, and then Yaw did a few protein networks and a Wikipedia network. But that's a pretty small sample of networks. So there's a lot of other things that could happen. Yeah. Yes?
At one point, you were trying to use the similarity matrix as the correlation matrix, and you said that if it wasn't PSD, you'd add identity to make it PSD.
Oh, what we did, no, we didn't do that. What we did is we were even cruder than that. If we saw a negative eigenvalue, we'd make it 0.
Okay,
Yeah.
so it's more of a cutting off.
Yeah.
Okay. Yeah, well, that was my question, actually. Were you lifting all the eigenvalues, or were you cutting them off and do you see?
We're just taking the negative ones and making them 0. It's a really Procrustean, we wanted it to be positive semi-definite, so let's do that. And I think it's like the closest in L2 norm to positive definite. So that was,
So, yeah,
Yeah.
good from that point of view.
so that, yeah. That doesn't mean that it's the right thing to do. And so there's 2 ad hoc steps. One, we ended up using a spline with I think 11 knots to smooth out the correlation versus similarity, and then we forced it to be positive semi-definite. So those are kind of ad hoc, and maybe there's something more principled that could fit in.
Okay, let's thank Art again, and we'll continue in the discussion.